Hello everyone, my name is Xuejian Wu. Today I would like to talk about my research of developing a quantum gravimeter and use it for gravity service. So here is a selfish with the gravimeter, and we were measuring outside a post office. We would like to set up a gravity benchmark. And a gravity benchmark is a place where you measure the gravity, and it could serve as a calibration spot and for other gravimeters, or as a reference spot and to study gravity or long time drift. So the problem is to measure absolute gravity, and the very simple idea is to drop something. And when you drop something, and you can measure how fast it accelerates, and that is the gravity. So here is a picture and show you how to measure that. And instead of dropping classical objects, what we do is to drop a bunch of items inside a vacuum chamber. And here is a picture that's after the laser cooling, and the cold item cloud starts free fall inside the vacuum chamber. And that's how we measure the gravity. Instead of directly measuring the timing and the distance, we try to form a microwave interferometer to increase the accuracy. Using this light and atom interaction, we create superpositions, and by measuring this atom population and these two superpositions, we can map out the interference fringes. And here is an example of the atom interferometer, and it starts from laser cooling to lower the temperature and increase the coherence length. And we need quite a lot of optics and lasers to do that job. And in our research, we invented a single laser system. There's no laser to laser locking. There's no amplifiers. Everything starts with a single laser, and using a few modulators, we can generate all the frequencies and intensities at different times. And here is the physics happens. That's the vacuum chamber. It's made by glass, and inside this vacuum chamber, there's a special designed mirror. And we are going to shoot the light and take advantage of the reflections, and to trap the atom and to do the atom-light interaction. After we build this gravimeter, it contains optics and electronics and the physics inside the vacuum chamber. And you use air river C into the vacuum chamber, you should see a picture like this, and where millions of cesium atoms were trapped inside this glass. And when it's free fall, and you start to measure gravity. So one example for gravity measurement is the tidal gravitational variation. And every location on the Earth will feel the attraction from the moon, and that will change over time. That's a tidal gravitational variation. So we measure that in the lab. That's the blue dots. Is consisted by a few jobs. And we compared our measurements with the solid Earth tidal model. We found the measurement and the theory has very good correlation. It's in a period of a few weeks. And as we averaging our measurement by every 2 hours to see with more sensitivity, and we found that at some time, and the measurement and the model actually missed a little bit, but sometimes, and they overlapped pretty well. And then we want to see why they missed, and we plot out the residue between the measurement and the theory, the solid Earth tidal model. We compare the residue with the water level variation in the San Francisco Bay, and we found that they are correlated, which turns out that we measure the second order effects of the tidal effects, which caused by the ocean loading. Besides the tidal variation during the long-term measurement, our gravimeter is sensitive enough to pick up small signals such as earthquakes, which happened in Asia. And we compared our results with the seismometer network. We get the measurements at the same time. And after we developed the machine, we did a few outdoor measurements. So here is a picture that we measure gravity on top of the bridge. And here we got a truck and load our machine, and we would like to drive it to the hill and do the measurement. So there's a Google map of our trip, which starts from this UC Berkeley campus and all the way up to the Berkeley Hills. And we selected 5 locations and stop and to do the gravity measurement. And in this way, we could get the gravity gradient over this trip. And here's a few pictures and on the trip, and we stop the truck and we do the alignment, make sure that the gravimeter is aligned with the gravity axis and to minimize this systematic effects. After the measurement, and we get off the truck and we're using a computer to control a microcontroller and run the machine. And we collect the data onto the computer and we let it run for half an hour and to averaging down the sensitivity to below 10 micrometer per second square. So here is a typical fringe that we get. By analysis the phase, we can measure the gravity. And each dot is the measurement and the cosine function is the phase. So our machine is limited by vibration noise. Large vibration can make the dots jump away from the feet. So here is a summary of our research. And by survey the Berkeley Hills, we get the gravity anomaly and we calculate the gravity gradient, which let us know the density of the hill. So here is my contact information, and let me know if you have any questions.